Today we'll talk about a new force, which is called Newton's universal law of gravity. So it's an additional thing that Newton did that he published along with his laws of motion that we've already talked about. And it's extremely important for the history of cosmology, the study of our universe. We'll talk about how this law of gravity, which is often written as F big G as opposed to F little g, which we've already studied. We'll talk about how that force can be used to understand the orbits of objects around planets, so satellites around planets or moons around planets. And we'll do a few examples of that in the later part of the lecture. But what I want to talk about first is just a little bit about cosmology, about how Newton's discovery fits in with sort of the history of our understanding of the universe. So we'll start there. So Newton published most of his important ideas in something called the Principia Mathematica, or the Principia Mathematica. I'm not sure how it's pronounced. He was English, but he wrote this down in Latin, and he actually, I think, wrote the entire manuscript in Latin at the time. So around the time that he was about 45 years old was when he published this. Of course, he did much of the work prior to that. And the things that were in this work were, of course, the discovery of calculus, which we've already talked about is the math that was needed to express the kinematics of objects. And calculus was also independently discovered by Leibniz, a German mathematician, and they had sort of a rivalry during their time, during their lives. And in fact, at the end of Leibniz's life, he was accused of having plagiarized Newton, although basically history has acquitted him. And in fact, if you go and learn calculus, the integral, the derivative, much of the language that we use in calculus is actually in Leibniz notation, as opposed to the work that Newton did. But they both discovered calculus independently during that time. So that was one thing in the Principia. The other, of course, is his three laws of motion, which we've talked about. Newton's first law, which you could call the law of inertia, or of inertial frames. The second law, the law that gives us forces causing accelerations. And the third law, the force of one object on another is opposite to the force of the other on the one. But the thing we haven't talked about yet is the universal law of gravity, and that was another extremely important thing to come out of this publication. And basically what he did is he used observations of the universe, astronomical observations, to derive a new force called the law of gravity, and then connect it to the thing that seems to pull objects down on the surface of the Earth. So he unified the gravitational force that we experience on Earth with the gravitational force that causes the motion of planets and moons. One of Newton's most famous quotes is this, which was written in a letter to Robert Hooke. Robert Hooke was also a physicist, and he is probably most famous for Hooke's law, the law for the spring force, which we haven't yet covered. What he said to Robert Hooke was, if I've seen further, it is by standing on the shoulders of giants. So he's explaining that yes, he has understood a lot about the universe, but much of his work is based on the work of others that came before him. It's actually thought possibly that this was a slight dig at Robert Hooke, who apparently was quite a short man, and so he was talking about the giants on which he has stood, maybe not including Robert Hooke. So I want to just talk a little bit about some of these so-called giants from cosmology in order to understand where Newton's law of gravity fits into the story of cosmology in general, our understanding of the universe. So I've shown here a few lifespans of some important people. So let's just go through and talk about some of these people and what they've done. So back here in 300 to 400 BC, or I guess I should say 400 to 300 BC, we had Aristotle. Aristotle was a Greek student of of oh geez, what's his name? Plato. Oh geez, what a blank. A student of Plato, and Aristotle, of course, talked about physics and about all sorts of natural sciences. But one of the things that Aristotle claimed was that the astronomical world, the world of the stars and the planets and the sun and the moon that go around us, which were well observed at that time, was something about the nested celestial spheres. And of course, in this model of the universe, the Earth was at center. So much of Aristotle's science, which really was more of a philosophy than a proven science, was about how the Earth was sort of the natural center of the world. We, people, were the center of the world. And then everything else sort of went around it, and that was the cosmology of the time. So there were these spheres that rotated around the Earth, and that caused things like the sun going up and down, and the moon going around us, and all of the stars going around us, and the planets as well. It was known that there were certain star-like objects which were obviously not the same as the stars. They were brighter and had sort of disks that were visible. And it wasn't until about 500 years later that I think I spelled that wrong. How do you spell Ptolemy? I think there's an E in here. That Ptolemy, also a Greek scientist, sort of quantified Aristotle's theory of the nested spheres. So we say that Ptolemy was the origin of the geocentric, meaning Earth-centric universe. So the idea was really Aristotle's, but it was more just philosophy. Ptolemy actually came up with some mathematical ideas about how you could actually place these spheres in order to get the observed motions of the planets. And it actually took a bit of work to make Aristotle's idea rigorous, because if you actually look out at the night sky, if you look at Mars over the course of time, you don't see Mars traveling in sort of a spherical orbit around us. You don't see a straight line orbit. Instead, what you see is that Mars every once in a while will sort of loop back on itself like this. And so Ptolemy had to try and understand that. And so he took this idea of nested spheres to an extreme and came up with an idea called epicycles. So there were sort of spheres within spheres out there, which allowed for these planets to maintain their orbits around the Earth, of course, which was at the center, but then create these weird orbits that you would actually see in the sky. So Aristotle's idea survived for a very long time, about 1,500 years or more, 2,000 years after Aristotle. It wasn't until the mid-15th century, or the late 15th century, that Copernicus, so this is Copernicus here, came up with the idea of a heliocentric universe. So his idea, which was not simply philosophy, it was based on careful astronomical observations already at the time, was that things would fit together better if the sun was actually the center of our universe, and the Earth was not. And this was essentially blasphemy at the time. Aristotle's idea of the Earth being at the center had been adopted by the Church, and so Copernicus basically kept his ideas hidden up until his death. So the publication of his book, which had an interesting name, it was called On the Motion of the Heavenly Spheres, or something like that. So he adopted the language of Aristotle, and the language of the church, in order to publish this very radical, revolutionary idea that the sun was the center of the universe. So the publication actually came in 1543, in the year of his death. And even though it was published only at the time of his death, he also had a preface which basically said, you know, these are just some mathematical ideas which I've seen in the data. I don't really believe these to be true, and they certainly have nothing to do with theology or our notion of where we are in the world. So it was sort of an apologetic presentation, but Copernicus's ideas led to a revolution in our understanding of the universe. And so this era here that followed was called the Copernican Revolution. And Newton was sort of at the end of that. So this is Newton here. He published his Principia at some point in the late 1600s. And he was preceded by Galileo, who we've talked about as influencing his laws of motion. And prior to that, Galileo and Newton both relied on some very important observational data from an astronomer named Tycho Brahe. Tycho Brahe was sort of the last of the naked eye astronomers. Galileo is probably the first to make important use of a telescope. And then Tycho Brahe took on a student later in his life named Johannes Kepler. And Kepler derived what are called the laws of planetary motion, which were basically just a really careful mathematical look at the data that Tycho Brahe had determined on the motion of the planets in our sky. So I want to talk a little bit more carefully about what happened during this Copernican revolution, but it's interesting to see that the Earth-centric universe is actually quite young in our history. It's only over the past 500 years that, the heliocentric universe is quite young. Prior to 1500, people believed that the Earth was the center of the universe. So what has happened since Copernicus? So this is Copernicus here, publishing his manuscript at death. Galileo, in 1609, of course, Galileo did many things, but the thing that I wanted to focus on was he observed the moons of Jupiter. And these are now called the Galilean moons. So the 4 brightest moons of Jupiter are called the Galilean moons. And this was really the first time that we had seen the orbit of objects around other astronomical objects. The geocentric universe was everything going around the Earth. But now Galileo, once he used his new telescope, could see that there were objects going around Jupiter. And Galileo's observations, along with Tycho Brahe's observations, allowed Kepler to derive his 3 laws of planetary motion. So let's just say what those are. So the first law, and these are really empirical laws, so they were just based on data. They don't have any sort of explanation or explanatory power like Newton's laws do. The first law that he came up with was that planets move on ellipses. So ellipses, one special case of an ellipse is a circle, and we'll talk about circular orbit today because it's a sort of easy case to do. But Kepler's careful analysis showed that every single planet orbited around the sun on not quite circles, on elliptical orbits, elliptical paths. The second law of his law of motion was something about equal areas in equal time. And we won't talk much about that, but just a little picture of that is this. If we have the sun in one of the foci of an ellipse, and then there's a planet which is going around that sun, then it turns out that the area that it passes through in any given time is the same for any equal time interval. So if you look sort of closer to the sun, it looks something like that for an equal time interval. And of course what that means is that the planet goes faster as it gets closer to the sun in order to sweep out an equal area, which might require a further distance traveled on its path. And then the most important of Kepler's laws, at least for what we'll talk about today, Kepler's third law, is period of orbit related to the radius of the orbit. So radius only works for circular motion, and it is that the period squared is proportional to the radius cubed. In Kepler's law, this is actually the semi-major axis of the ellipse. So that actually means sort of the half size of the ellipse. For circular motion, we can just think of it as the radius. And again, this was just something that was found from the data, particularly from Tycho Brahe's analysis of planetary motion through the sky. So Kepler's work, in particular this third law, led to Newton's law of gravity. And we're going to look at that in detail in the next section, how Kepler's idea of period squared is proportional to radius cubed leads directly to Newton's derivation of the law of gravity, the force of gravity. So this was Newton here. So that sort of ended the Copernican revolution. There were people that sacrificed a lot in order to make this change from a geocentric to heliocentric universe. As I said, Copernicus basically hid his life's work until his death so that he didn't have to deal with the challenges from the church. Galileo, and along with Kepler and Tycho Brahe, they celebrated Copernicus's work, and Galileo actually was placed under house arrest for many of the last years of his life by the church for these heretical ideas, the ideas that the Earth was not the center of the universe. By the time of Newton, we had really an explanatory theory for the universe, the way that objects move around each other. All of Kepler's laws, all of these laws that I wrote down here, were then explained by Newton's law of gravity. So we will only really talk about the connection of the law of gravity to Kepler's third law, but the elliptical motion and the equal areas, equal times can all come out of Newton's laws of motion and also Newton's law of gravity, although the mathematics is a little bit too difficult for us to look at. But of course, Newton's laws didn't end the theory or the study of cosmology, what's going on in our universe. So I want to talk a little bit about what happened afterwards in more modern times. So in 1915, Einstein developed or presented the complete work of his theory of general relativity. So the theory of general relativity basically replaced Newton's law of gravity. In fact, it said that Newton's law of gravity doesn't actually exist. And the way that it replaced it is that it theorized that if you have an object like the sun, then the sun sits in something called space-time, which is really the combination of time and space put together. And the sun effectively bends space-time, and that bending of space-time will cause something like the Earth to take a straight path on a bent surface, which actually looks like a circle if you sort of look at it in projection. So if you can imagine sort of a plastic sheet with a bowling ball put into it, then you can imagine rolling another ball, like a tennis ball, around that bent sheet, and it would follow a circular motion. That's effectively what Einstein's theory of general relativity says. So there is no gravity, there is no Newtonian gravity, but instead our space-time is bent by mass, which allows for things to take what seem like circular orbits, but are actually straight orbits. And this is our current theory of the universe, of how objects move in relation to one another. And this theory has led to a new revolution in the 20th century and now the 21st century. And some pieces of that are, well, in 1925, Edwin Hubble came up with the idea that the nebulae are galaxies. So these things had been seen out in space, things that were not stars, but looked like sort of clouds out there in the sky. And what Edwin Hubble discovered was that these discrete clouds were actually galaxies, just like the one in which we lived in, some collections of stars which sit out at a distance from our own galaxy, which we call the Milky Way galaxy. And this was actually a very controversial idea only 100 years ago. But he gave good evidence for the fact that, for example, the Andromeda galaxy was a galaxy that was very similar to our own, but some 25 million light years away from us. And he followed up this work in 1929 with an explanation of the motion of these galaxies. And in order to understand that motion, we should step back one moment to something that happened in 1908, which was a discovery by a woman named Henrietta Leavitt. She was at Harvard Observatory after graduating from Radcliffe College, and she found this special class of stars called Cepheid variables. Not certain that I've spelled that correctly. A Cepheid variable, she found, is a variable star, meaning a star that changes its brightness over time, and the period. So if you were to look at the brightness over time, then the period of that brightness, so this is a little t, time, and this is a big T, period, is actually related to the absolute brightness of the star. So the main problem in astronomy is that we look up at this two-dimensional surface of the sky, and there are stars of different brightness, but we don't know if those stars are bright. One star is brighter than another because it is closer to us than the other star, or because it is actually more luminous, that it puts out more light than the other star. So being able to disentangle the difference between brightness and distance is an extremely important thing in astronomy. And what Henrietta Leavitt found was that there are certain stars, Cepheid variables, in which you could measure the period of the brightness changing, and that would give you exactly the absolute luminosity of the star, the absolute brightness of the star. And once you know the absolute brightness of a star, then you can compare it to its apparent brightness on Earth, to know its distance. So we can compare the distance of these stars. This allows you to find the distances of stars both locally in the Milky Way galaxy, but also in other galaxies. So Hubble later found that there are other galaxies, and Hubble used Henrietta Leavitt's idea to show that, so we can call this the Hubble expansion, to show that if you look at a bunch of different galaxies, then their speed with respect to us, so their v, is related to the distance from us. So for galaxies that are not that far away, their speed is small, but for galaxies that are far away, their speed gets larger. And one can find basically a proportionality here, which is called the Hubble law, which says that as you look further out into the universe, objects are traveling away from us at a faster speed. And that constant, which is called the Hubble constant, is actually the inverse of the age of the universe. So the idea is that why would you get objects to be traveling away from us at a further distance, traveling faster away from us at a further distance? Well, you can imagine that these galaxies are sort of sitting on the surface of a balloon. So these are a bunch of little spiral galaxies, maybe. And as you inflate that balloon, so maybe the balloon gets to here, then the galaxies will sort of get further apart, obviously. But the ones, if we're sitting here, the ones that are closer will move away more slowly than the ones that are further away. And that's because the rubber of the balloon is expanding the same at every little piece, but there's more rubber between a distant galaxy than there is between a nearby galaxy. So the speed of a galaxy as that balloon expands will increase as you get further away. And this is basically the model of the expansion of the universe. Of course, if you go backwards on this picture, so you go backwards in time, then what do you get? Well, you get just a little tiny balloon, and that we call the Big Bang. So our observations of the universe today, which show us that galaxies are expanding, but galaxies are expanding faster away from us as they get further away from us, leads to this idea that at one moment in time, all of the matter of the universe was compressed into a single point, which we call the Big Bang. And that's effectively our theory of cosmology today, which is that we came from this moment, the Big Bang, which happened something like 13.6 billion years ago. So that started with the work of Hubble back in 1929. He was the one who first observed that some galaxies were going away, and it has continued throughout the 20th century. In fact, during this period here, there was confirmatory work using what are called supernovae. So just like a Cepheid variable, there are certain exploding stars called type 1a supernovae, which explode with the same brightness every time, meaning the same absolute brightness, the same luminosity, which means that when you see one of these things explode, and it has some characteristic way that it explodes so we can identify them in other galaxies, then you know exactly how far away that supernova is, and you know how far away the galaxy is, which allows you to make this Hubble law more carefully. So supernovae have been used, and actually something else happened just in the very end of the 20th century, in 1998. We found that there was an accelerated expansion of the universe. So Hubble showed us that the universe was expanding, but this careful look at supernovae actually gave us a new Hubble law. So let's take a look at what that looks like. So the Hubble law, again, is that the speed of objects increases with distance, and we say that that's basically a proportional relationship. So this is the Hubble law, and if you look at nearby galaxies, you see that they fit very nicely along here out to very distant galaxies. What the supernova data showed us is that if you get too far away, what you see is that they start to go like this, meaning that it's not really a proportional relationship, that actually things that are getting further away start to speed up even more. So this is an acceleration. And effectively, we don't have any idea why that's true. There's a word for this, which is called or phrase, which is called dark energy. But effectively, dark energy just means we don't know why this is happening. And that's actually the current state of cosmology. We don't know is a pretty good summary of what's going on in cosmology. We know that the universe is expanding. We know that there was a Big Bang, but we don't have any idea why the universe is starting to expand more quickly now. And in fact, there's a paired dark quantity, which is called dark matter, which one can see using Newton's law of gravity. If you look at a galaxy, so if we have some, for example, spiral galaxy that looks like this, and you look at some star out on the edge of that galaxy, you can try and understand its orbit based on how much mass is contained within its orbit. And if you just look at the stars that appear there in that galaxy, you can calculate that mass, and it turns out that the star on the edge is actually going way too fast as compared to the amount of mass inside. So there's a bunch of missing mass inside of every galaxy that we look at, and we call that missing mass dark matter, meaning matter which does not appear as stars. And in fact, lots of careful observations have been done, and it's actually matter that doesn't appear in any way whatsoever except for its gravitational effects. So it turns out that dark matter is something like 96% of matter. So 4% is, stars and galaxies and baseballs, things that we understand. 96% is dark matter. And then dark energy, so this is only 25% of the mass and energy in the entire universe. The rest of it, 75%, is dark energy. So 4% of everything in the universe is understood. It's the stuff that makes up matter. The rest of it, almost all of it, is not understood. Part of it is dark matter. Part of it is this dark energy, which causes the acceleration of the universe. So that's sort of the where cosmology is, where our understanding of the universe is today. And it all goes back to Newton's law of gravity, which basically explained the most fundamental principles of the universe, which were that there are orbiting objects around other objects, not just things that go around the Earth, which was given to us by Copernicus back in 1543. So that's history. Let's talk a little bit more about gravity and about what Newton actually did. So I've put a couple little pieces of Newton's Principia here. And one of the things that he had in the Principia were data tables. So data that he'd gotten, for example, from Kepler that looked carefully at, for example, the moons of Jupiter. So these are the Galilean moons of Jupiter orbiting around Jupiter. And what was shown in this were the period of those moons as a function of their orbital radius. And you don't actually have to measure that in meters, you can just measure it as compared to the radius of the Jupiter itself. And that's what this data is. I plotted it out. And what Newton showed, well actually what Kepler showed, was that if you plot this out, so I've plotted it as a log-log graph. So this is the log of the period of the moon in days versus the log of the radius. And if you have a power law relationship, then you get a straight line on a log-log graph. So this red line here is a straight line fit that says that t is proportional to r to the 1.5 power. And Newton calls this a sesquiplicate proportion. So t proportional to r to the 1.5, well that is r to the 3 halves. And then if you square both sides of this, you get t squared is proportional to r cubed, which is Kepler's third law of planetary motion. So Kepler's third law of planetary motion was shown in Newton's Principia in this nice data table here. And Newton used that to derive his law of gravity. So let's go through that argument because it's very nice. So let's draw out Jupiter here. So we'll use Jupiter as our example, although Newton used some other objects as well. I think he used the motion of the planets around the sun because Kepler had good data for that as well. But here's Jupiter. And Jupiter had a number of moons that went in basically circular orbits around it. So here's one. And we can say, well, it has some velocity, some speed as it's going around. And Kepler basically just gave us the relationship between the amount of time that went by. So what is that? Well, that's the period. And the period should be related to that speed and to the radius of its orbit. So what is the relationship? Well, its speed is equal to distance over time, which here we can say is the circumference, 2 pi r, divided by the period, t. So Kepler was able to relate the amount of time that it took for a moon to go around to the radius of its orbit. And that was Kepler's third law. What Newton did, now that Newton had the laws of motion, well, Newton knew that if something is to travel in a circle, there must be, well, first of all, we know that it has an acceleration, which points inward. We learned that in the last lecture, that circular motion requires an inward pointing acceleration. That's kinematics. Newton's dynamical law, the second law of motion, says that if there's an acceleration, there must be a force which causes that. So Newton said, okay, my own second law tells me that there is some force, and we don't really know what that force is. Some force that causes the moon to accelerate in its motion around Jupiter. Well, so what does Newton's second law tell us then? Well, let's just write it down. So F net is equal to ma. In our free body diagram for the moon, we only have one force. It's this unknown, questionable force, F question. And we have a problem of circular motion here. So we could find the center of the circle and draw the radial axis. There's one more axis there, the tangential axis. We can break up our equation into the radial equation. So we get F question mark radial is equal to ma radial. And then we have an expression. Well, first of all, let's write this out. This is minus the magnitude of that unknown force. And AR, we know, is minus v squared over r. So what's the point of this? Well, Newton knew that in order for an object to travel in a circle, there must be a force causing it to do so. And what he did was he used this expression to determine all the properties of that force, to effectively write down the equation for that force. So what does this give us? Well, first of all, we see that the magnitude of this unknown force is equal to mv squared over r. But with Kepler's law, we can actually, well, first of all, we can use this expression for the speed and the period and the radius to give us that this is m over r times 2 pi r over the period squared. So what does that lead to? Well, it's something like 4 pi squared m r squared over r is just r over the period. So this is the magnitude of that unknown force. But now comes Kepler's law. So Kepler told us that the period squared was proportional to the radius cubed, and this actually is period squared down here. I lost it when I took the square. So I can just replace period squared with radius cubed, or a constant times that. So we get a constant times radius cubed, and we still have 4 pi squared m times radius in the numerator. So we get 4 pi squared m over k times 1 over r squared. This is what Newton found. He found that the magnitude of the force that caused the orbit of moons around planets was proportional to, number one, the mass of the the orbiting moon, and also proportional to 1 over the radius squared, the distance of that moon from the center of the planet. So what do we have? Well, if we call this the gravitational force, we see that its magnitude is equal to some constant, which we can call big G. It's proportional to 1 over r squared. Actually, let's call that a little r squared. It's proportional to the mass of one of the objects. But then by Newton's third law, we know that there should be a force of the moon on the planet as well. And if you go through the whole process, then you should arrive at the same type of equation, but with the mass of Jupiter in there as well. So the force, which must be equal on the moon and on Jupiter by Newton's third law, must be actually the product of the masses. So it has to include the mass of Jupiter as well. So we have a gravitational constant. Now, Newton didn't actually know the exact value for this at the time, but we found since that it's something like 6.7 times 10 to the minus 11 in some units. This R is the separation of M and capital M, so meaning the distance between their centers. And then you have the product of the masses, and that is the force of gravity. So let's write out that force completely. So the force of gravity is equal to a force with magnitude gmm over r squared, and it is attractive, so the direction is attractive. And this is what Newton found. So it's nice to just check and see how he did this. We had an empirical relationship from Kepler that related period to radius, and then Newton was the first to be able to derive the actual force law because he invented forces. He invented them through his laws of motion, and his laws of motion, along with kinematics, told him that there must be some force causing this orbit. And then from these little steps, including the insertion of Kepler's law at this point, we find that that force is a 1 over r squared law, and it's clearly an attractive force based on the necessity of the acceleration pointing inward. So we have a law of gravity. This is called the universal law of gravity. The next thing that Newton did in the Principia was to argue that this force, this universal law of gravity that causes the orbit of moons and planets, is actually the same thing that causes objects to fall towards the Earth, on the surface of the Earth. So he gave this cute little argument here, which I won't go through the whole thing, but he says, suppose that there are several moons to revolve about the Earth, just as in Jupiter or Saturn. Of course, we only have one moon, but he's saying, well, let's let there be some other ones. And then if we take one that's very, very low and very, very small and allow it to just orbit by touching the tops of the highest mountains, then the thing that causes it to go around is, of course, Newton's universal law of gravity, the thing that we just derived. But if you were to stop it from its motion, so it wasn't able to go with a velocity parallel to the Earth anymore, then that force would cause it to drop down to Earth. And so that's what this deserted by its centrifugal force. If you stopped it from rotating, then it would descend to the Earth. And it would descend just like any heavy body that was sitting up there at the top of the mountain would do. So his argument is, if the gravitational force that was holding it in orbit is different from the gravitational force that causes objects to fall, then in fact it would fall with twice the velocity or twice the acceleration of some just falling object on the mountain. And therefore, that's ridiculous. It must be exactly the same thing that causes it to fall as causes it to retain its orbit. So therefore, the force which retains the moon in its orbit is the very force which we commonly call gravity, because otherwise this little moon at the top of the mountain must either be without gravity or fall twice as swiftly as heavy bodies are wont to do. So he unified the force that causes the orbit of moons around planets and of planets around the sun with the thing that we call gravity on the surface of the Earth. So let's look at that connection. So if we use Newton's universal law of gravity to understand what is pulling us towards the surface of the Earth, then we should be able to understand what F little g is. So here we are. Maybe we have some little mass m, and then there's the mass of the Earth sitting underneath us, and the center of the Earth is down here in the middle of this sphere. And we could say that the separation of our two masses is little r, but it's just equal to the radius of the Earth, because we're standing on the surface of the Earth, and the center of the Earth's mass is down at the center of the Earth. So what is Newton's universal gravity acting on us? Well, it's equal to big G, little m, big M over r squared. That's the magnitude of the force of gravity. And for the case that we've drawn here, that is big G times little m, your mass, times the mass of the Earth divided by the radius of the Earth squared. And I've written out these quantities here so we could plug them in to see what their values are. So let's do that. So we have, well, let's bring the little m out front, and let's calculate big G times mass of the Earth divided by the radius of the Earth squared. So let's type that into the calculator. So what do we get? Well, we have big G is something like 6.7 times 10 to the minus 11. The mass of the Earth is 5.97 times 10 to the minus 10 to the 24 kilograms, and then divided by the radius of the Earth, which is 6.38 times 10 to the 6 meters. We want to put everything in SI units, and squared. And what I found in my calculator is I have little m times a number which is 9.8 meters per second squared. What is that? Well, that's what we call little g. So our law of gravity that we had on Earth, which was F little g is equal to m little g, is actually just a special case of the universal law of gravity. It's the special case where the separation of the objects is exactly equal to the radius of the Earth, and the mass of the second object, well, that's the mass of the entire Earth. So there's an attractive force of the big Earth pulling on us, which is F big G. Of course, by Newton's third law, there's also a force of us pulling on the Earth, F big G, but we only feel the one that's pulling on us. So F big G is F little g, just for the special case of standing on the surface of the Earth. Okay, we'll do 3 examples now. The first one, we'll just calculate the force of gravity just to sort of see what its magnitude looks like. We did one example just now. If you have the whole Earth pulling on you, then you get a force which is equal to your weight, m little g. What if we try to calculate the force of Lake Michigan pulling on you? So, well, let's just sketch it out. So Lake Michigan looks something like this, and then Michigan, oops, I guess I shouldn't use. So here's Lake Michigan, and then we have Michigan, Lower Peninsula, looks like this, right? And maybe you're standing over here in Western Michigan, and you have little m right there. And then big M, let's call the mass of Lake Michigan. We'll place its sort of gravitational center at the sort of, well, it's called the center of mass, but we haven't figured out what that means yet. So we'll place the center there. And then the separation of these two is maybe, I don't know, 100 kilometers, something like that, or maybe 50 kilometers. Depending on how close to the shore you are. So that's our R value. And what is big M? Well, Lake Michigan is something like, it has a length of maybe 500 kilometers. And it has a width, sort of an average width of maybe 120 kilometers. And it has a depth, I looked this up, the average depth is something like 85, let's just say 100 meters. So very thin compared to its length and width, but quite deep. So what do we get from that? Well, the volume of the lake is going to be length times width times depth. And then the mass of the lake can be related to its density. So the volume in meters cubed can be turned into a mass by multiplying by a density, which is in kilograms per meters cubed. And here we have just the density of water, and that density is actually, it has a very nice value because we basically based our units of kilograms off of it. It's 1,000 kilograms per meter cubed. So once we calculate the volume, then we can figure out what the mass is. So let's just calculate that. The volume of the lake is L, 500, and that's times 10 to the 3 to get us meters, multiplied by the width is 120, also times 10 to the 3, multiplied by the depth, which is 100 meters. So we get a volume of 6 times 10 to the 12th meters cubed. So that goes here. And of course we find multiplied by 10 to the 3, we get 6 times 10 to the 15th kilograms. Sort of an unimaginably large mass, 10 to the 15 kilograms. That's the mass of the lake. So what is the force of gravity on U? So force of gravity on U in magnitude is going to be big G times big M times little m over the square of the separation. And that's big G times the mass of the lake times the mass of U times divided by the distance, which we just called r here, squared. And let's say that the mass of U is maybe 60 kilograms. So what is that force in newtons? Well, we can plug it in. So we have the mass is 6 times 10 to the 15. Multiply that by the gravitational constant, which is 6.7 times 10 to the minus 11. Multiply that by your mass, which is 60 kilograms. And then divide by the distance, which we said was 50 kilometers, so that's 50,000 meters, and we square that. So we get about 9.6 times 10 to the minus 3 newtons. That's Fg. Well, that should be equal to mg. So what's that in mass? Well, it's just you divide by 9.8, and we get about, so that means that the mass is something like, if this force were to be the weight of an object, that would be some mass is equal to about 1 times 10 to the minus 3 kilograms, or about 1 gram. So what does that mean? Well, we take as a given that the lake is pulling on us. So there is a force of the lake on us, which we call F big G. It's the force of the lake pulling us towards it, and we want to see what that feels like. Well, it's about 10 to the minus 2 newtons. That's what we found here. And if we were to convert that into a weight of some object, then that object would have a mass of 1 gram, Well, that's about the mass of a paperclip. So Lake Michigan is tugging on us, but it's exactly how much the whole Earth tugs on a paperclip. So we don't really feel it. We do feel the force of the Earth tugging on us, or at least we feel that in relation to the normal force. That is our weight. So when you calculate the force of the entire Earth pulling on you, you get mg, you get your weight. But if you calculate something else, something smaller, even if it's as big as Lake Michigan, then it's effectively completely negligible. You would never feel it, the weight of a paperclip pulling on you. So you can imagine how small the force of, for example, your neighbor sitting next to you would be on you. Because then, in that case, you'd have two 60-kilogram masses, and this would get much, much smaller. So this attractive force of objects is only seen when you have enormous objects pulling on each other, like the Earth pulling on you, or like a planet pulling on a moon. So we'll study some of those next. So let's look at the circular motion of a satellite around the moon. So we're going to do problems, orbital problems like this, using Newton's law of gravity. And we're going to restrict ourselves to the motion of circular orbits because it makes the problem easier. I mentioned up above that Kepler's law says that objects travel, the orbit of objects around the sun and planet and moons around the planet follow ellipses. A circular case is a special case of that, and it's the only one that we can do really easily mathematically. So let's take a look. So we have a moon, the moon, I guess our moon, so there are little craters on it. And then there is a satellite, maybe one that we sent up, and it is orbiting around the moon like this, and we'll take it to be a circular orbit. So the distance from the center of the moon to the satellite, well, we need to figure this out, I guess. It's going to be the height of its orbit plus the radius of the moon. So let's figure out what that is. Well, the radius of the moon is 1.7 times 10 to the 6 meters. So that's 170 kilometers. And then we're told that the circular orbit is 200 kilometers. So it's about, the radius is about twice the distance to the center of the moon. So this is going to be, so let's call this this is our moon. And then h is going to be 200 kilometers. So let's put h in here in our picture. 200 kilometers there. So the distance that we're looking at, and let's actually call it, let's go bigger. The radius of the orbit is h plus the radius of the moon. This here is our moon. Now, in order for this object to travel in a circle, it means that its velocity is constantly being bent inwards by an acceleration. We know this from circular motion. So there must be an acceleration there. And in order for an object to have an acceleration, by Newton's second law, there must be a force on that object. And we now know that that is the force of gravity, which we call F big G. So let's do Newton's second law here. So we have F net is equal to ma for the satellite. That's our m right here. This is m moon. In our free body diagram, we only have one force, which is Fg, F big G. And this is a circular motion problem. So we want to choose an axis which goes outward from the center of the circle. We call that the radial axis. You can put some other axis on there as well. And in the radial direction, we get FGR is equal to MAR. Well, FGR is pointing inward on the radial axis, so we get minus the magnitude Fg. And AR, well, that's the whole reason we chose a radial axis, because we know that the radial component of the acceleration for circular motion is minus v squared over big R. Big R is the radius of the orbit. Okay, so we get F big G is equal to little m v squared over R. What is our question? The question is, what must be the orbital speed of a satellite that's in a certain circular orbit? So are we able to solve this yet? Well, let's plug in for Newton's law of gravity. So we have big G is equal to big M, and big M in this case is the mass of the moon, times little m divided by the distance between the centers of the objects, which is what we're calling big R, squared, is equal to little m v squared over big R. It's interesting here, these two R's are the same, but they had a different meaning. So here this was the center of the circular orbit, and here this R is the separation of the two objects. But as you can see from the picture, those two things are the same. The center of the circular orbit is the center of the moon, which means that it's the distance from the satellite to the moon. So we can solve this, and we can solve it because even though we weren't given the mass of the satellite, that cancels out, and we can get expression for v. We can also multiply both sides by one of the r's, so we get that v squared is equal to gmm over r, where v is equal to the square root of big G, mass of the moon, over r, and we said that r is the height of the orbit plus the radius of the moon. So we can plug that in. Let's do it. So we get 6.7 times 10 to the minus 11 for big G. We multiply that by the mass of the moon, which is 7.4 times 10 to the 22nd. We divide that by the quantity of the height, which is 200, well, times 10 to the 3, plus the radius of the moon, which is 170, times 10 to the 3, to put it in meters. And it is not squared because we canceled out some r's there. So that, and then we take the square root of that. And we find that the answer is 3,660 meters per second. So if you send a satellite up there around the moon, and it has an orbit of 200 kilometers above the surface of the moon, then it must be traveling with exactly this velocity, almost 4,000 meters per second, or about 3 kilometers per second. Let's figure out what the time is for it to go around. So the period of its orbit is related to its speed by, well, v is equal to distance over time. In this case, that distance is the circumference, as we talked about just on the previous page. The time is what we call the period of its orbit. Remember this t with the special bars on it we call the period. And therefore we can find the period from the speed as period is equal to 2 pi r over v. So let's figure out what that is. Well, it's 2 times pi times that quantity 200,000 plus 170,000 meters divided by almost 4,000 meters per second, and we get 635 seconds. Well, what is that? Well, divide that by 60 to get to minutes, and you get, so 635 divided by 60, so that's approximately 1 minute, no, 10 minutes, approximately 10 minutes. So a satellite at that orbital height will take about 10 minutes to go around the moon. We're going to do another exercise, but you'll see as we go through these examples that there's really only a few things that we're using, so it's probably good to point that out. So we're using Newton's second law. We're drawing a picture of the orbit, we're drawing the two objects which are attracted to each other by Newton's law of gravity, and we're drawing a free body diagram. We're using circular motion, which we learned last time, so we show the inward pointing the acceleration, we use the radial axis, and we use the expression for the radial acceleration in order to relate Newton's second law to the law of gravity. So we plug in the law of gravity here. In this case, we just solved from there for the unknown, which appeared in our equation. But one additional thing that we might need to use is this expression for the speed as related to the distance, which in particular can be written in terms of the period and the radius of the orbit. So these are really the only tools that we need in order to do these type of orbital problems with Newton's law of gravity. We'll do one more. So it turns out it's possible to place a satellite in a circular orbit around the Earth such that it remains above the same point on the Earth as the Earth rotates on its axis. So meaning you could place it above sort of the longitude of Grand Rapids, and that satellite would stay there in orbit around the Earth, but from the perspective of Grand Rapids, it would stay at exactly the same point in the sky. And that's because the Earth rotates on its axis, while the satellite would rotate around the Earth. So let's try and draw a picture of that. So maybe this is the Earth, and let's say that this is what it looks like from above. So if we were to draw, how do we draw this? I guess Alaska looks sort of like this, and then there's North America, and here's Florida, North America, then here's Europe, and then this is Russia. Oh dear, Russia is very far away from Alaska in my picture. Anyways, we're looking down on the North Pole here. I guess I should have just drawn the North Pole here. So here's the North Pole. We're looking down on the North Pole of the Earth. And then we place a satellite to orbit around the Earth. It turns out that in order to make this orbit, you must put it around the equator, because the Earth is not a perfect sphere. It's sort of bulged, so you need to place it around the equator so it doesn't feel the imperfections of the Earth's gravitational pull. It will have some orbital radius, r, and the idea is that we want it to have some velocity, v, such that if it's sitting above some point on the Atlantic Ocean, and the Earth itself is rotating around with some angular velocity about its pole, then these things will stay exactly oriented together. So this connection will be the same as it rotates around. I don't really know how to draw the rotation, but as this goes around here, then this will go around here. So the question is, how big do you have to make r in order for that to be the case? So we do exactly the same thing as we did in the last problem. We do Newton's second law. So we know that there's a single force acting on the satellite, and that's F big G. We know that that is causing an inward pointing acceleration, and this is a circular motion problem, so we draw an axis pointing outwards from the center of the circle, the radial axis. Here's the tangential axis. And we write down Newton's second law. So we have F net is equal to ma. We only have Fg. And we look at it in the radial direction. So we have Fgr is equal to mar. And just as last time, we have inward pointing Fg, so we get minus the magnitude is equal to m times minus v squared over r for our centripetal acceleration, which leads to, if we plug in the equation for Fg, well, it's big G times the mass of the Earth times the mass of the satellite divided by r, that is the radius of the orbit, is equal to m v squared over r. And again, the two r's mean exactly the same thing. One is the center of the circle, the radius of the circle. The other is the separation of the two objects' centers, but that is the same for a circular orbit. And I left off a squared here. So I guess our boxed equation to come out of Newton's second law, again, we can divide both sides by m, divide both sides, or multiply both sides by big R, and we get big G, mass of the Earth, over R is equal to v squared. same as we had last time. But we have a different question here. So the question is, what is the r such that we get a geosynchronous orbit? So what does that mean? Well, it means that the period of the orbit, the amount of time it takes to go around, should be exactly equal to 1 day. And that's because we want the satellite to come back to the same place on its orbit at the same moment that the point on Earth comes back to the same point on its orbit. And that is what we call 1 day, the amount of time it takes for the Earth to go around. So what is 1 day? Well, that is 24 hours times 60 minutes per hour times 60 seconds per minute. So we can get that in SI units. So what is that? It's 24 times 60 times 60. So that's 86,400 seconds. So we want a period to be exactly 1 day on Earth, which is 86,000 seconds. Well, how does that relate to what we found already? Well, the period, remember, is buried inside of the v here. So we have v is equal to distance over time, but in the case of a circular orbit, the distance is the circumference and the time is the period. So we can replace over here, v squared is going to be 4 pi squared r squared over period squared, and then we have g, mass of the Earth, over r. So what do we get? Well, we're looking for the radius of the orbit. That's what we want to find. Everything else is known. So let's plug these things. Well, let's not plug them in. Let's solve first. I'm going to solve it 2 ways because it's interesting. You can see if I solve here for t squared, multiply both sides by t squared and then divide the left-hand side off, what do we get? We get 4 pi squared. R squared times r is going to be r cubed, and then we get over gme. Did I do that right? I think so. Well, what is that? Why did I do that? Doesn't tell us what we want yet. I did it because it's Kepler's law. Third law. So we used Kepler's third law to derive the law of gravity, so it's not a surprise that we should be able to get Kepler's law back now that we know what the law of gravity is. But you see that Newton's third law now exactly predicts Kepler's third law, which was just an empirical observed relationship, and it also predicts what the constant is. So Kepler just said that there was a proportionality. Newton says, well, take my gravitational constant, also plug in the mass of the object that's being orbited around, use a 4 pi squared in there, and you'll get the constant. Okay, but for this problem, we're not interested in that. For this problem, we're interested in what r is. So if I solve that for r, I get g, mass of the Earth, over 4 pi squared times t squared. And then I have to get rid of that cubed, so I take the whole thing to the 1/3 power. So now we can plug in. So we have 6.7 times 10 to the minus 11 for the gravitational constant. The mass of the Earth, got to go back up and find that. Oh, I don't have it there. I did put that somewhere, didn't I? Mass of the Earth. I did, up here. So the mass of the Earth is 5.97 times 10 to the 24 kilograms. And then we divide by 4 pi squared. And then we multiply by the period, which is 86,000 seconds. And we square that. And then we take the cube root of it. We take that to the 1/3 power. And we get 4.2 times 10 to the 7th meters. So what is that? Well, that's about 42 times 10 to the 6, which is 42,000 kilometers. So where do we place this thing? Well, the Earth has a radius of about 6,000 kilometers. So the radius of the satellite is going to be at 42, about 7 times that. So about 7 times this radius. So 1, 2, 3, 4, 5, 6, 7. So the satellite is way out here. So a geosynchronous orbit requires that the satellite is put out at 42,000 kilometers around the Earth. And in fact, we use this all the time. So communication satellites and weather satellites that want to take pictures of the same location on the Earth, they're all placed out at this geosynchronous orbit radius at 42,000 kilometers. That's compared to things like the International Space Station, which are really only a couple hundred miles above the surface of the Earth. So even where I've drawn it is too far out. Things like orbiting manned spacecraft are right next to the surface of the Earth. The geosynchronous orbits are way out there. So I hope you see the methods here. We're basically just using things that we already know: Newton's second law, circular motion with a radial axis. The only new part is that we're plugging in the force of gravity, and then for orbits we're making use of this relationship between speed, distance, and time on a circular path there. Okay, see you next time.